So here we have another example of a mole conversion problem. It says what is the volume of 12.24 moles of neon at standard temperature and pressure? If you recall, this is important. At standard STP, 1 mole of gas will occupy 22.4 liters of volume. Okay, so hopefully you have that somewhere in your notes. All right. Well, I want to do this using a few strategies. Unless a strategy is dictated for you by your instructor, I would use the first method that I'm about to show you. Okay, so you just have to please your instructor based on what he or she wants. But if they do not specify, use this first method. All right, so method one is the easiest one I can think of. It really is you're just converting moles to liters, and liter is the measurement of volume. So the problem gives you 12.24 moles of neon at STP. So I'm going to start with 12.24 moles. I'm going to put over that a sexy 1 that I like. You don't have to. I just like to put it over a 1 so it gives me a visual of a whole fraction. I have a numerator and a denominator. And then from there, I can just use this conversion factor in red that hopefully you have, again, somewhere in your notes. I'm going to put moles on the bottom because I'm starting out with 12.24 moles. I need to cancel out the unit moles, so moles has to go on the bottom. And then therefore liters has to go on top. Well, 1 mole is 22.4 liters. So as you see here, moles cancels out on the top and bottom. So the only unit left over is liter, which is what I want because they asked for volume. Here, as you can see, the only thing we have to do is really just multiply across. So 12.24 times 22.4 liters, and that'll give us our answer. The bottom is just a 1. Like 1 times 1 is just 1, so it doesn't really matter in this problem. So this is the easiest and quickest way to get this one done. So the answer is going to be 274.2 liters, or about, right? Method 2. Method 2 uses ratio. What ratio? Well, using the conversion factor. Here I have my statement. 1 mole is 22.4 liters on the left side, equals to 12.24 moles. And what is this volume that will occupy? So the way to read it is, look, if you have 1 mole, it takes up this much space, right? 22.4 liters. Therefore, if you have 12.24 moles, how much space will it take up? The ratio must remain the same. So essentially, I hope this makes sense without overcomplicating it. This is 1 mole. To get 1 to equal to 12.24, you have to multiply the numerator by 12.24. Well, if you do multiply the top by 12.24, you also have to multiply the bottom by 12.24. That's how I would do it, just using common sense. However, I will show you how to do this solving the question mark algebraically. Okay, so in my next step here, I'm just going to go ahead and replace the question mark with the variable. Again, I like x because x in mathematics is your unknown. But you notice here x is in the denominator. So when you're solving for a variable, it cannot be in the denominator. You have to get it into the numerator. So I think for this particular problem, the quickest way to get it, is just to switch x and mole. So I'm going to move x up to the top left. At the same time, I'm going to move the 1 mole down to the bottom right. But if I move x to the top left, I still have this 22.4 liters on the left side. So I'm going to move the 22.4 liters to the top right. Or in math, they like to say multiply both sides by 22.4 liters. So you notice here this arrow is a one-way arrow, okay? So I'm only going to move the 22.4 liters up. So if you do that, the only thing on the left side of the equal sign is x. The 12.24 moles, I did move this 22.4 liters up to the right, which is right here. And then the 1 mole from top left, I moved it down to the top right, which is right here. So it's just a quick little switcheroo for these types of ratio setup. All right. So as you can see here, you have 12.24 moles times 22.4 liters over 1 mole. The unit moles cancels out. And then that leaves you with x, which is equal to 274.2, which is the same answer that we previously get in method 1. So I will take method 1 all day, okay? Because I think it's quick to do and it's the easiest one to do. All right. Method 3 is for it's for you in case your instructor is trying to teach you the ideal gas law. Well, the ideal gas law is PV equals nRT, right? In this case, we're solving for V because it asks for volume. So in order to solve for volume algebraically, you need to divide both sides by P. So you notice here, P is on the left side. I'm going to divide both sides by P, which brings it down to the denominator on the right side. nRT hasn't moved. I just added a division sign because P is now in the denominator. Well, if your instructor encourages you to use this particular method because you're working with the ideal gas law, then you should know these constant, right? You should. And if you don't, you should touch base with your instructor. Here, N represents the number of moles. Well, the number of moles is given in the problem. It says 12.24 moles. So for N, I'm just going to write 12.24 moles. For R is your constant. And R is a little tricky based on what your instructor gives you. You have to go with it. Here, R, one of the versions of R is 0.08206 liters times ATM, which is the measurement of pressure, moles times Kelvin. K here stands for Kelvin. And then at standard temperature, T is simply 273.15 Kelvin, right? And then if you're going to use ATM variation of R, then the bottom, P would just be 1 ATM. The standard pressure at sea level is 1 ATM. So you notice here, because I'm using an R variation that uses ATM, my pressure on the bottom is 1 ATM because that's standard. Therefore, if you do this properly, moles cancels out, right? The ATM on the top, ATM on the bottom cancels out, and then Kelvin on the bottom, and then Kelvin for the 273.15 units of Kelvin also cancels out. So the only unit left over is liters. So therefore, this is how you know you're doing this right. If you punch all this up in your calculator, you should get about 274.4, which is slightly off from what we got, right? Earlier, we got 274.2. And that's because this strategy here that I'm presenting, method 3, uses R, which has a lot more decimal, and everything else has more decimals to it. So, but I mean, to me, it's the same. 274.4, 274.2, whatever, all right? The chemistry is the same. All right. However, method 3 can also be applied using a different constant. So this is where, if you're beginning, you could be a little confused. There are variations of this R constant based on the units that's presented to you. So here, I want to go ahead and do another way for you. N still represents the number of moles, which is 12.24 moles. R in this case, I'm not going to use this variation of R. I'm going to use 8.314 liters times kilopascal. So I highlighted here this coefficient, which is different than the coefficient in the previous method, right? Both are using ideal gas law. It comes down to which R constant is your professor and instructor emphasizing. If he or she does not emphasize one, pick one and be consistent, right? So this is 8.314 liters times kilopascal over moles times Kelvin. So the only thing that's different here is the units of measurement of pressure. You can measure pressure in atmospheric pressure, ATM, or you can measure in Pascal or kilopascal. Well, here, what I've written down in the bottom is for pressure, this is as standard temperature and pressure, it's going to be 101,325 Pascal. Well, this is kilopascal. This is Pascal. They both have Pascal, but one is in kilo and one is in Pascal. So to me, it's a super easy conversion, right? Mole's going to cancel as usual. Kelvin's going to cancel out. But the only thing you got to pay attention to here is to be able to use kilopascal and Pascal. You got to make sure they're both the same unit. So here, I want to convert the denominator, Pascal, into kilopascal so that I have kilopascal. Well, I'm going to start with 101,325 Pascal. And I want to convert it for every 1,000 Pascal. And 1,000 Pascal has to go on the bottom here because you're trying to cancel out Pascal, PA. And then on the numerator, you have to write 1 kilopascal, right? So if you do this, it makes sense. So 101,325 divided by 1,000, really would just shift the decimal place 3 spaces to the left. So your answer is going to be 101.325 kilopascal. So I'm going to write the same step here, except I'm going to keep everything in the numerator the same. And the only thing I'm changing is the denominator. So instead of Pascal, I'm going to write it as kilopascal. So this is a comma, this is a decimal. So in units of kilopascal, it is only 101 kilopascal, right? Or 101.325 kilopascal. So kilopascal is not going to cancel out. And therefore, if you punch all things in your calculator, you'll get the same value of 274.3 liters. Again, the decimal place here at the very end is going to be slightly off only because we're dealing with different decimals based on the strategy that you're using. But like I said earlier, unless a method is dictated for you, I would use method number 1. I hope that helps. Stay nerdy, don't be whack.